we're going to talk about tree health during drought, and a fair amount of what I'm going to be talking about is just kind of general concepts of tree health, because I think kind of understanding a lot of the basic forces and things at play really then helps us understand why certain recommendations might help. So, there we go. This is me, just a little bit of background. The main point of all this background is I have spent my life around, thinking about, learning about, and working with plants and trees. It's just a passion of mine. I think I was an ant in another life. That's me in my preferred habitat, my natural habitat, barefoot in the back garden. So again, I have a lot of plant sensibility, I think. I like to often start with definitions because it's a good place to make sure we're all kind of on the same page. And when we think about trees, there's a lot of different ways to define what is a tree. So some might say, well, it's a large, woody, perennial plant. And yes, they are. But is that big shrub a small tree, or is it a big shrub? Size may vary. They are large plants with lots of leaves, and that's an important concept because when it comes to water use, leaves are the place where water leaves the tree and enters the atmosphere, and there's a lot that goes on there. So simply the fact that it's a big plant with a lot of leaves does mean it's going to use a fair amount of water. That's a biological reality. Trees are typically found in regions of higher precipitation, so I've thrown up a little bit of a map there that shows kind of the normal annual precipitation in different parts of this country. And the blue and the green are more moist, and you get into the yellow and the red, and obviously it's more dry. Sometimes those trees exist in dry landscapes, but if they're natural trees, they're existing in the wetter parts of those dry landscapes. So along rivers, in higher mountain areas, things like that. And really importantly, trees are sedentary organisms. Given a choice, they will never get up and move. Now, in urban tree reality, we move trees all the time. And so that has a lot of impact on how roots develop, and that has a lot of impact then on how the tree can maintain its health. And trees, interestingly enough, are also social. There's a lot of really good research coming out in the last couple of decades that is starting to uncover the ways in which trees communicate with their neighbors, either of the same species or different. And so we need to not think of them as just this inert part of the landscape that we can plug in and take out. It's a living organism in a living environment. So here's that precipitation map, okay? Kind of keep this in mind as we go to the next map, which is going to show you where historically there have been forests in this country. And it tracks the precipitation map really, really closely. What we see as we get past the Mississippi River is that trees are found along rivers, and they're found at higher elevation. And that's a reality all of us who live in New Mexico understand, but we don't always apply that to our landscapes, and we'll talk about that. So here's a little group of friends in a city park. We've got a redwood, we've got a pinon, and in the middle we have a blue spruce. And they are all sharing root zone. They're communicating through the root zone. They're communicating through the air with different volatile chemistry. There's a lot going on in this seemingly stable and slow-moving system. So let's then kind of dive down into what do trees need to be healthy. And there's a few things. They need to be able to photosynthesize. Plants feed themselves. They, in quotes, eat the air. So they are taking in carbon dioxide and using the energy of sunlight, they're breaking that carbon dioxide apart and they're creating sugars. That process requires the presence of water in a few ways. One, it's part of the chemical reaction, so we got to have it as an ingredient. Another one is that this chemical reaction takes place inside a cell environment that is kind of moist, an aqueous cell environment. So water is involved there. And then water is also involved in gas exchange. So the way leaves work, they're taking in gas through tiny openings in the leaf surface. And as the CO2 diffuses in, water vapor diffuses out. And it turns out that about 90% or more of the water that comes into a tree simply passes out through those openings without really having a function other than that inside the tree. So there's this stream of water. A talk I heard one time, the speaker described trees as organisms that have figured out how to insert themselves in the physics of water moving from high concentration in the soil to low concentration in the air. They just channel that natural process and take advantage of it, which is brilliant. Well, what else do they need? Obviously, they need water in order to be able to photosynthesize. They need nutrients as well. And this is a whole suite of nutrients that are involved in building up all of the different chemistry inside the tree, inside whatever kind of plant that is needed. So they're getting nitrogen, phosphorus, potassium as macronutrients. There's some mid-level nutrients there. There's some micronutrients that are needed in tiny quantities, but they are needed. And all of these, except the carbon and some of the oxygen, are coming in from the soil with soil water. So not only does the root system need to be taking in water, but it's also, by taking in that water, taking in the nutrients that are in that soil water medium. All right, what else do they need? Well, they need sunlight, right? That's the energy that powers the whole photosynthesis process. They need it to be the right temperature, not too cold, not too hot. That varies by species. But there are a lot of things that, the Albuquerque area is too hot for. And there's some things that our winters are too cold for. And so those things matter. They need space. They've got to be able to have enough space above ground that they can have an array of solar collectors out there, the leaves, taking in sunlight. But they also need a lot of space below ground for the roots to explore. What's kind of interesting is that, by and large, canopies don't tend to integrate too much. But below ground, root systems go everywhere. Everybody gets to go anywhere they can. So there's lots of crossing and whatnot. And that allows for some of the root-mediated communication that trees take on. And that's what they need, is they need that social environment that they are a part of. Other trees and plants to communicate with. And a lot of that communication is done through certain fungi, specifically mycorrhizal fungi that we've pictured over here on the right-hand side. Mycorrhizal fungi are interesting. So the little tiny white filaments are the fungal growth, the hyphae. That big pale blob that they're wrapped around is a root tip. So they are so much smaller than roots, and they're able to explore places in the soil that roots can't. And they're able to pull in water and nutrients that the plant needs. They bring them into the plant cell, and basically they barter with the plant for sugars made by photosynthesis. So it's a really nice economy below ground where both partners are benefiting. It's a great symbiotic relationship. What does all of that have in common? The soil. The soil is so fundamental. That 6 to 12 inch layer of living soil over the planet is really what makes things work. It's the environment for roots, obviously, and root function and root health are primary for tree function and tree health. There's a number of ways in which roots are primary, and I think we're talking about them later, so I won't bring them up right now. Soil is not just an inert dirt. Yes, there's non-living mineral particles in there, quite a bit, but they form a matrix in which organic matter exists, both living and dead, water exists, and air exists. And so all of those things come together in that magical environment that we call the soil. And it's really the key to good plant health. Soil is really easy to harm, and it's hard and slow to heal. So what we do to soil really matters and is reflected in tree health. All right. There's an unhealthy tree right there in that picture. This is a London plane sycamore in the North Valley. And the owner who had this property before the people who had it during the time I took the picture, the previous owner gardened like a maniac, had plants and stuff growing everywhere, used a lot of water. Subsequent owners came in from out of state, didn't realize we have to irrigate if we want to keep big trees healthy, even if we're in the valley, and they stopped, and things took a downturn for sure. Now, that's kind of what a tree is, and just a little bit about how they function. We'll get into that a little bit more. What is drought? How do we define drought? Well, if you look it up on Wikipedia or in a dictionary, it's basically drier than normal conditions, okay? And a drought can be days long, months long, years long, but it's drier than normal. So what is normal for us? Well, it's pretty low. 8.8 inches is the average precipitation, annual precipitation over a 20-year average in the Albuquerque area. That's basically desert, okay? In 2023, we only had 5.8 inches. So drought is very relative. If we're back in the eastern part of the country where it normally rains, 40 inches a year, drought is 25 inches of rain that year. For us, 25 inches would be way more than we've ever had. So drought is relative to what is normal for the area. All right, well, we're in a desert. So already there's some issues of water availability. And even in normal good times, if we want to grow large trees successfully in almost every landscape, we are going to need to irrigate. There are those weird exceptions that basically prove the rule, but you're not going to grow big trees in Albuquerque area without some kind of decent irrigation. As we look at the picture, we see one of those pine trees is very, very brown. That's a drought stress response. The other ones are not looking so droughty, so that one might actually be a drought stress response to a compromised root system or low trunk. That's a whole nother issue. But that's what drought produces. It produces dead tissue above ground. So, in good times, we need to irrigate. In an actual drought, like 5.8 inches of precipitation in 2023, we need to irrigate more to replace that which we've lost from natural sources. Or maybe we just need to be more effective and efficient with our irrigation. Maybe we are using enough water, we're just not using it well. So here's a question. Do we have periodic droughts, or do we live in an environment that's the equivalent of a drought? And the answer to both is yes. We live in a desert, and sometimes it's way drier than normal. So those are just realities. And back to the fact that, trees are big plants with lots of leaves. They're going to use a lot of water. They have to. And so that's why you don't see trees growing naturally in our area outside of places where there is some available water, or with a few exceptions, things like tree of heaven and Siberian elm. Sometimes I see those growing where I have no clue where they're getting water. Sometimes it's fugitive water. Amos mentioned that concept, and I think a lot of our trees do get by on leaking sewer lines and leaking water lines, fugitive water in the soil. All right, so we've got drought that produces some stress for trees. Heat is another big stressor, and we have a lot of that too. So we get a lot of tree stress. Some trees are able to do things themselves to reduce the stress of drought. And so a lot of those strategies are aimed at just, again, simply reducing water loss by reducing transpiration. Transpiration is the term we use for when water leaves the leaf. It's basically a kind of evaporation from the high water environment inside the leaf to the relatively low water environment in the atmosphere. So if you can shut down transpiration, you'll reduce water loss. Unfortunately, shutting down transpiration usually involves closing those little openings. So think of the evaporative cooler that you may have at your house. I have one at my house. The way they work is that evaporating water absorbs heat and cools. So if I'm reducing that water evaporation, I'm not cooling. So leaves get hotter and hotter. And sometimes they actually get too hot. And then the internal biochemistry breaks down and function is reduced or even stops. So let me move this out of my way a little bit so I can read. So around the world, and certainly in the Western US, we're seeing a lot of it. As the climate is warming, droughts are becoming more common and heat levels are rising. And we're seeing huge swaths of natural forest dry out and then often burn up because of that lack of water combined with increased temperatures. As you increase the temperature of the air around a leaf, you make that air more thirsty and it can evaporate even more water from that leaf. Okay. So then we get to urban trees. So there's wild trees and there's kept trees. And the kept trees are often starting out in worse conditions. The soil is usually compacted. The root system is usually deformed because it's been in a container. But there is the advantage of people who want to grow a tree and understand that they need to take care of it, including watering. So how do trees take in water anyways? Well, again, they're kind of organisms that have managed to put themselves in the middle of a natural flow of water from moist soil to dry air, and they channel that flow and they use it for their own benefit, which is brilliant. But it first comes into the root system through tiny, tiny roots, root hair sized and small absorbing roots that are so small and young they don't yet have bark. And they're basically sponges. So the water in the soil is pulled into that spongy root material, and then it moves into bigger and bigger roots that have bark. Those roots with bark don't lose water, but they also don't absorb water. So the absorption is happening in these tiny, tiny roots, millions of them, scattered throughout the root zone of the tree, feeding the larger roots that then ultimately go up into the vascular system of the tree and up into the leaves. If those young roots live long enough, they may actually develop some bark and become something more than an absorbing root. They're more of a support root. Or they may simply die off. There's good evidence that over the course of a season, you may get multiple flushes of fine root growth when there's water in the soil, and then fine root die back when the soil dries up too much. And then there's another big rain event and the roots grow out again. And so there's a lot of dynamic growth and dieback happening in the soil that way. And all of those dead roots, by the way, add organic matter to the soil. And organic matter is key for both nutrients and the soil's water holding ability. So those young roots dying off, it's not a bad thing. It's just part of the cycle. So the small absorbing roots, again, they're found where moisture is consistently present in the soil. They're found much farther from the tree trunk than most people think. I often think and speak in analogies, and one of the analogies I like to use is to compare roots and water molecules to roads and cars. So the big roots that are close to a tree trunk are moving water pulled in from a vast array of small roots. There's a lot of volume. The big roots close to the trunk are like interstates. A lot of water moving fast. But nobody, and so back to the analogy, that's kind of like a highway system, right? And the cars with people in it are like the water molecules coming in. Well, nobody starts their morning commute in the middle of the freeway doing 65. You start in your driveway, and from your driveway you go to the feeder neighborhood street, and then into the bigger local street, and finally you're in the freeway. Well, similar to that with tree roots, the absorption is not happening right close to the base. There's a little bit of fine roots there, but there's not very much, and certainly not enough to take care of all the water uptake needs the tree has. More than a million tiny mouths out there drinking water. And this is a really key point where plant life and animal life, like us, differ. When I'm thirsty, I take in water through one large main opening, my mouth. Trees don't have mouths. They have a million tiny rootlets spread broadly through the soil. So if I apply my water in one spot, the roots that are over here don't get any of it. And the roots that are in that one spot may not be able to take in as much as I put there. And what this speaks to is we need to distribute water more broadly through the landscape. This is a great picture that I took at UNM, actually, one day when I just happened to go out there, and the head arborist at the time, Brian Sewer, had directed his staff to dig this large tree out of the soil because it was going to get a building put on it, and its other fate would be death. So they dug it up with an air spade, blew all the soil off the roots, and moved it. And what I really like about it is it shows how roots are long and thin and ropey. And there's a whole interesting side discussion of several hours about why that is, but we won't go into that. But it also illustrates that root architecture is very different than stem and branch architecture. One example that I heard at a talk again was, think of a wine glass sitting on a small plate. The goblet of the wine glass is the tree's canopy. The stem of the wine glass is the tree's trunk. The base of the wine glass is the root collar in close, where there are some big roots because they also are holding the tree up. But then you get to the plate itself, and that's fine, long, ropey roots that are basically acting as anchors to that whole structure. Well, how do they take in nutrients then? They're taking in water. It's just being absorbed into these fine roots. And it's the loss of water from the leaves, by the way, that creates a suction that then pulls that water that just came into the roots up into the plant. What about nutrients? Well, they're coming in with the soil water, okay, unless they're carbon dioxide. And one of the cool things that plants can do, the way that water is held onto soil particles involves some electrical charges, and plants can basically take a hydrogen atom, split off an electron, and then push that now positively charged hydrogen ion out into the soil, where it can bump one of the mineral nutrients off that absorption point. And there's a picture coming up that will help explain that. A key point. Soil chemistry is exceedingly complex. And there's so many things that influence it that even the best soil scientists only know a small part of the big picture. There's so much going on down there. But here's kind of an example. The big brown mass is the soil particle, and it has a lot of negative charges on its surface, especially if it's clay, or if it might be a large bit of organic matter. It's going to have these charges. And most of the plant nutrients that are in the soil exist as positively charged ions. So there's a positive to negative attraction between the nutrient ion and the soil particle. It's not a real strong attachment, but there's an attachment. So if those nutrient ions can get into the soil water, then the plant can take them in. And again, that's where those little H plus circles, those are hydrogen ions the plant has pushed out into the soil to bump some of that stuff out of its attachment to the soil particle so it can get into the soil water and come into the plant. Again, it's not just a passive thing happening below ground. There's strategy and technique involved. All right, the vascular flow of trees, water's coming into the roots. It gets into what we call the xylem tissue, which is basically cells that are like straws and that are connected end to end, and water can be pulled through those from the farthest root all the way up to the furthest leaf. And that water loss from the leaves, again, is kind of the suction on that column of water that pulls it up into the tree. During the nighttime, when there's not a demand of water's not evaporating out of the leaf, in part because during the night, when there's no sunlight, the plant will close those little openings because it doesn't need to take in CO2 because it doesn't have light energy to process that CO2. So it kind of shuts down, but it's still less water in that leaf than in the soil, and so there's still kind of a replenishment that happens during the nighttime, assuming there's moisture enough in the soil. But if that soil is too dry and that replenishment can't happen quickly, then plants can experience some water loss stress. And honestly, many plants in Albuquerque live in a chronic low to medium level lack of water stress. It's just part of how they live. So again, some of the trees will close those leaf openings, which we call stomates or stomata, as a way to reduce that water loss. Some trees, especially trees that are adapted to a dry season, so they may be tropical trees, but there's a wet season and a dry season, they will be drought deciduous. They are programmed that when it gets too dry, they actually let the leaves drop and they just shut down for a while until there's enough moisture to start up again. Other plants, especially those that are evolved in high water environments, they don't have mechanisms to close the leaf openings enough. They don't have mechanisms to let those leaves drop intentionally, so they just continue losing water until there's just collapse of the whole system. All right, at the leaf level, again, 90% of the water that's coming into that root system is simply lost through the leaf due to evapotranspiration. But that allows the plant to keep those little openings open, and CO2 can come in, and oxygen, which is a byproduct, a waste product almost of photosynthesis, can leave. If the leaf couldn't get rid of oxygen, it might build up to a poisonous level. Oxygen is extremely reactive, and yeah, that could be a problem for sure. So that evaporative cooling keeps everything at a temperature where it can function and things are good. So take home there is leaves have to be able to lose water in order to function properly. And during drought, this is either challenged or completely disrupted. And that's what trees have to deal with, and that's where we can really help them. Our goal in those situations is to have enough water in the soil that the tree can kind of stay in business and keep itself alive until the baseline conditions get better. But remember, our baseline conditions are desert by and large. And so it doesn't mean that, as soon as the rain starts, let's say we get a good monsoon season, that we can completely quit watering. We might be able to quit for a little while, but we're still going to have to pay attention. So trees are responding to drought by closing their stomates, which again, less water out means less carbon dioxide in. So while they're preserving what they have, they're not adding to. And if they have to completely close those stomates, they're losing, because every living cell in that tree is using energy just to stay alive. It's like an idling engine. Even if the car isn't moving, the engine is running and gas is being used. Those living cells are using energy, but the tree is not taking in any more energy. So hopefully it has enough of a bank account to keep that going. It also leads to heat building up, right? And a lack of photosynthesis means we're not getting sugars. So once closing the stomates is not enough, they can drop leaves. And as important as leaves are to plants, and they're critical, they are absolutely critical. They are the source of food for leaves. They're also about the most expendable part of the whole system, especially deciduous trees. They drop their leaves every year anyways. And leaves can be rebuilt and replaced pretty readily when the resources are available. So a tree can be defoliated and not necessarily be in huge trouble. Again, some trees have a drought dormancy if they're evolved in that kind of a landscape. Some trees will root deeper to find water in, again, traditionally kind of dry, droughty landscapes. Siberian elm seems to be able to do that real well. It's a very deep-rooted tree. And I remember years ago looking for an image of Siberian elm to use in a presentation, and I came across an image from part of its native range, the Gobi Desert, and it was nothing but rocks and sand and one small green tree. It was a naturally growing Siberian elm. They're incredible. But that's a very species-specific trait. Not all trees can do it, and the soil has to be an appropriate soil. If it's really dry down below anyways, or there's like a caliche layer or some kind of compaction, they're not necessarily going to be able to root deeper. And, I've talked to clients before who, let's say, lived in the mid-heights, and I'm telling them, oh, your tree is thirsty. And they're like, well, but it's established. It should be getting all the water it needs from the water table. Well, if you're in the mid-heights, the water table is probably 700 to 800 feet below you. Those roots aren't getting there. All right. So things go on. It gets worse. The leaves decline, then they die and they're lost. And we can also get embolisms in that vascular system, in those straws, where a bubble appears as that column of water is stretched too strongly. And where embolisms occur, it can really mess up future water movement up that. We can get heat stress, we can get root death, and we can get tree death. So there are things trees do to try to weather a drought, but they also respond to drought by declining and dying. Here's a couple of examples of ways that this can happen. So on the left-hand side, we have what I believe was once a purple leaf plum. It was planted as a street tree, and it was not well irrigated. We can see how much dry, hot soil there is around it, and that tree is basically just up and died. The tree on the right is a catalpa. When that tree was planted, that entire front yard was turf, and the tree grew well. And then at some point, a homeowner said, hey, I want to be responsible. I want to reduce my water use on turf. And they reduced the turf to an inner core, and they graveled the outside edge. Well, as we've just talked about, it turns out that a lot of the fine roots that absorb water are found near and even well beyond that outside edge. So once this catalpa began to get drought stressed and the roots began to die back, then the root system was invaded by a fungal disease called verticillium wilt. And that verticillium wilt is largely responsible for the thinning and ultimate death of this tree, the thinning of the canopy and the ultimate death. It would have happened by drought stress alone at some point, but because the fungus grows in and plugs up vascular systems, it exacerbates drought reaction quite a bit, speeds it up a lot. All right, phew, that's a lot of stuff. It's some kind of basic science, but I really kind of want to help folks understand that trees are living organisms with their own biological realities, and we can't ignore those and expect good results. All right. So one of our goals, especially during drought, is to maintain sufficient soil moisture. And we're going to start with the idea that, again, all of our urban trees are going to need supplemental irrigation in the best of years. And so that has to be part of the approach. And so this is where we get into how are irrigation systems designed. Well, the key is we need to be able to get the water to where the tree needs the water to be. And I've been heard to say that a lot of irrigation that I see is great plumbing because they got the water where they thought it needed to be, but it's horrible horticulture because that's not actually where the water needed to be. And so understanding how root systems grow and function allows us then to design our irrigation system to the best ability. And that all comes back to where are those absorbing roots. So the biggest mistake that I see around here and other places that I visited is that we don't put out enough emitters and we put them way too close to the base of the tree. Now this often happens at planting because the tree is small, the root system is artificially small because it's either been in a container or it was dug out of the ground and made into a ball and burlap. And so initially we do need to water close to the tree because we have to get water to where the current roots are. But pretty quickly, if that tree starts to get established, those roots are going to grow out to and then beyond the edge of the canopy. And we need to move the water out with the root growth, and actually moving the water out helps the root growth occur as it should. And if we are successful, every year that tree is bigger than it was the year before. It has more leaves than it had the year before. Therefore, it is using more water than it did the year before. And so we plant something like a sycamore. We put 2 or 3 emitters at the base. For the first couple of years, everything's great. And then it starts to look thirsty. And then by year 10, the tree is dying because we are still only watering it minimally. Right at the base, we are pouring water into the interstate and we're not getting it into the flow. All right. Distribution. We need to distribute that water throughout the root zone. One of the things I've taken to telling clients lately is a 3-step thought process. First step in the thought process, trees need a certain volume of water. Second step, that volume of water available to them depends on the volume of soil holding water. Third step is the volume of soil holding water is entirely dependent on the surface area directly receiving water. So again, I can take the required amount of water, put it all in one spot, drown those roots, and everything else is dying of thirst. Trees don't drink the way we do. They don't have one mouth right there at the base of the tree. They have a million tiny mouths scattered throughout the root zone, and that's how we need to approach it. So here's 2 different ways to set things up. On the left, we have a fairly young tree planted, and at the very base of the tree, you can see a little white dot right next to the ground. That is actually the bubbler for this tree. So it's getting water from one source, the bubbler. Well, look how small that tree is and how close to the trunk that bubbler is. And imagine the tree growing a little bit more, and pretty soon it's pushing that infrastructure aside. It may break that line. Now that water is just flowing out as a flood at the root, at the base there, but it's not covering very much soil surface. So in order for those roots to really maximize water uptake, they got to stay right there around the trunk. This leads to a less stable tree, a tree less resilient to drought, and it may actually lead to the growth of what we call stem girdling roots. These are the tree's own roots that grow so tightly around the trunk that as the trunk tries to expand, the root acts as a noose and can actually kill the tree. Over on the right, we have a different setup. These are some young trees in a backyard, my backyard. And this is several years ago. When I moved in, the prior owner had run a water line out by each tree and just poked 2 holes in that line next to each tree. And they were growing, they were alive, but I put in drip tubing. So all of those black lines have emitters built in every 1 foot down the way. So I'm getting water distributed broadly throughout that landscape. That particular set of trees also happens to benefit from rainwater harvesting off of my roof. As it comes down on the right side or the left side of that picture, it flows out and basically just surface flows throughout that entire root zone. I've since planted a bunch of understory plants and then mulched it with wood chips. We'll get to all of that later as well. But those trees are doing great. So I've thought about this a lot. How do we help people understand? How do we understand what is the kind of best target zone? And so with a theoretical tree that has equal root volume in all directions, I kind of imagine a donut. And the donut is dry in the middle, right there at the base of the tree. And the irrigation starts maybe a third or a half the way out to the edge of the canopy, away from the trunk. And then it goes the same distance beyond the edge of the canopy if it can. Now that's going to capture a really good amount of the root space that is likely to be hosting absorbent root growth. And again, those flushes that grow and die back and grow and die back. You can see some of the roots I've drawn going well beyond that prime irrigation zone, but we don't need to target every root, and we can't really see where they are anyways. So this gives us kind of a model to shoot for. So again, dry at the center, goes out halfway to the drip zone, and then the same distance beyond. Now, the reality is that very few landscapes are that ideal. We may have lots of root volume on one side, and the other side there's a house or a street, or there's a house and a street, and now we only have even less root volume. So in that case, what I try to do is imagine that amount of surface area arranged asymmetrically and differently to fit the landscape that is available, because that's how the roots will have grown. They are going to grow. Roots are pioneers and explorers, and they search out and follow moisture in the soil. And when they hit dry and hard soil, they don't proliferate there very much. They tend to turn. So they're going to be in that landscape where they're best supported. Another approach might be something like this. The blue lines are all drip irrigation tubing. So there's a central ring around the trunk, not right up on it, not too far out. And then there are individual lines of drip tubing running out radially away from the tree. This is good, but it leaves a lot of dry spaces in between the arms of that radial structure. But at least it's getting water fairly broadly throughout the soil. All right, so different ways to water then. There's a lot of different ways. And I just threw together a little table here of pros and cons. Sprinklers, they do have pros. They mimic rainfall. You get a broad distribution across the irrigated area, and those drops are often oxygenated, and roots, it turns out, need oxygen. And so sprinklers are great because they mimic rainfall. They're not great because that rain-like pattern is easily blown off target by the wind. It's easily evaporated by dry, hot air. And if there's a surface flow, if there's a slope, we may get surface flow and get that water running down the street, like Amos was talking about earlier. So, you know, if a sprinkler is already what you have, there are ways to work a sprinkler effectively for trees. It's going to be using the sprinkler much less often, but longer, and really paying attention to when you do it so you don't have high wind or real hot temperatures, and making sure you're paying attention to any off-target flow. The next thing we have is the garden hose. The pros about a garden hose is cheap. The cons are you really, really have to be paying attention to where you're placing it, how it's flowing, making sure it's not overflowing, making sure it's not eroding the surface. But if you have the time, you can do decent watering with a garden hose. Soaker hoses, pros there, they're inexpensive, and you get that broad distribution if you lay it out well. And you're not going to get very much evaporative loss at all. You can put it under mulch and get even less. But the typical soaker hose is basically just an extremely porous tube with tiny, tiny pores that weep water, and they clog up real easy with grit, with mineralization from our water, and they're not very durable. They're, especially if they have been in the sun at all, they just disintegrate. What about drip emitters? Well, pros there, they very precise application. You can get that water right where you want it to be. It's very efficient. You don't have the evaporative loss. You don't have the wind loss, that kind of thing. The downside I've seen to drip emitters is that nobody puts out as many as the tree needs. Again, at planting, a handful of drip emitters at the base is adequate and sufficient to keep the tree alive and get it growing. But pretty soon it has outpaced that and it becomes insufficient. Drip tubing is my preferred approach. You get the precise application and the efficiency of drip emitters, but because the main tube line itself is also the emitter, you don't have to plug in little spaghetti tubing running all over the landscape. You can lay it out in a really nice pattern, and it lasts a lot longer than soaker hose. Now, it does cost a fair amount more, and you really got to think through how you're going to set up the system, and it's you got to make sure that you are preventing backflow into the municipal water system. You got to filter it. You got to reduce pressure. But those aren't actually very difficult. They're pretty easy to set up. Finally, I'll speak to flood irrigation just because for some folks it's an option. If you're down in the valley and you're on an acequia that runs, when it's available, you can flood the heck out of a large area. So you get broad coverage, you get deep soaking. That's all great and it's cheap, but it's a really limited resource in terms of who's got access to that. You have it or you don't. And that's kind of how it works. This is a question that is challenging to answer. There's a lot of questions about watering that are actually pretty challenging to answer. So how often do we want to water? My favorite answer, it depends. The soil type can have an impact on that. If I've got a very sandy, gravelly soil, it's going to absorb water very quickly, but it's going to let that water pass through very quickly as well. So that sandy, gravelly soil is going to dry out sooner than if it was a clay soil. Clay soils can take in a lot of water, but they do it very slowly and they hold it well and they hold it long. And sometimes they hold it so well that the plant cannot extract it. So let me back up and just on those two issues. I like to think that if I'm growing the same kind and size tree in a sand soil and a gravel soil, over the course of a year, I will probably apply the same amount of water to each, but the pattern will be different. On the sandy soil, I will water more often, but less water each time because it's not going to stay in the soil. It's going to percolate down out of root zone and it's lost. In a clay soil, I'm going to water less often, but I'm going to add more water when I do. So clay soil, I might water that tree every 2 weeks. Sand soil, I might water it twice a week. The root depth matters. When we grow trees in turf, and I used to work for the city as a city forester, and most of the trees I dealt with were in park turf. We water for the turf. Turf needs more frequent watering, but it doesn't have to go as deep. Turf roots aren't very deep. So then the trees growing in that soil, their roots grow where the water is, and they grow very shallow. And there's just not a lot of resiliency in that kind of a root system. If we can water a little less often, but broadly and deeper, then the roots will occupy a deeper profile. They will occupy more volume of soil, and you won't need to water as often. But when you do, you'll need to put more water on that soil. So, very roughly, and with all kinds of exceptions, this is one way to think about it. When things are dormant, I do recommend watering once a month to maintain a baseline level of moisture in the soil so that when dormancy breaks and growth starts, the tree isn't immediately drought stressed. During the growing season, maybe 2 to 4 times a month, especially in the early part of that season. And again, this is assuming that you can water broadly and deeply. The more constrained the root zone is, you're going to have to water a little more often. Or depending on the tree type. I've got fruit trees in my backyard. I typically water twice a week on those during the growing season. If it's really hot, we might even want to buck that up a little bit more frequently because the tree is just simply moving more water. And depending on the soil coverage, there may be more evaporation from the soil as well. So again, here's on the left, this was a cottonwood tree that no longer exists, but when it was growing, its roots grew right there on the surface. Now, that might have been turf, or another common situation where we find roots growing on the surface is when there's some sort of a weed fabric, or especially a solid plastic weed barrier under some kind of a mulch. Water will collect and form a thin film on the bottom side of that weed barrier, and the initial root growth, the tiny roots exploring the young tree's environment, will follow that water. And so they're right there at the surface. On the right-hand side, this is a young tree that we planted last year. We actually bare rooted it. We took it out of the root ball carefully with water, removed all the soil, and then took it up and planted it. It's an elm, and it's already got more of a downward angling root system. And now we are planting it in turf, which again typically is not watered real deeply, but we talked to the homeowner and they have set up an irrigation system where they are periodically pushing a deeper pulse of water into that soil that's a little bit more for the tree than it is the turf. There's another issue. Roots absolutely have to have oxygen in order to metabolically function. Otherwise, they asphyxiate. So sufficient soil oxygen is a goal. And this is why, one reason why we really, really, really do not like plastic sheeting as a ground cover. It is not permeable. Gases that build up in the soil, so the roots are down there, they're metabolically functioning, which means they're using up oxygen and they're giving off CO2. And if those gases can't equilibrate with the atmosphere, we end up with an anoxic condition and root function stops. When they make me king, and I know that's a questionable thing to say in today's political climate, but if I were the king, I would outlaw weed fabrics of any kind. First point is, they're really bad at stopping weed growth. Second point is, they're really good at interrupting organic matter getting into the soil. So then they start to break apart and surface, and it's just ugly. So We don't want those. We want to limit soil compaction in order to keep soil oxygen. So soil, again, it's a mixture of mineral, of organic matter, of water and air. And the water and air are held in pores, in openings in that soil. When we compact the soil, we crush those openings and we just reduce the ability of that soil to hold water and oxygen. So it reduces those pore spaces and it makes the soil so dense that roots can't really penetrate it as they're trying to grow. So just a couple more examples. On the left, this was a tree that had a plastic sheet under gravel, and you can see how that root just grew right under the plastic sheeting and made it over to the irrigated turf in the neighbor's yard and then got happy. On the right-hand side, this was a site I visited earlier this summer where very recently, within the last 2 years, a landscape nursery company had put plastic and then crusher fines over what had been organically mulched planting beds. And we're currently working up a bid for this rather large building. It's a federal property out in Gallup to go in and undo all of that, because that is going to lead to tree decline for sure. And then just back to the idea that it's unsightly. Most of the white that you see on the ground there is weed fabric that has surfaced out of the mulch and is deteriorating. And it's just frankly ugly. So there's that. All right. Phew. Got to take a drink of water here. And I hope I'm not going too fast. I hope I'm not lingering too long. It's difficult in a webinar setting like this because there's no direct audience reaction to judge my pace at or anything. So I'm just going to continue. Tree health is all about the roots, and roots are all about the soil. So again, growth, health, survival require energy in the form of sugars that the tree makes from sunlight and air, and that takes water, and that water comes from the soil. And roots are the part of the tree taking in the water and the nutrients. So there's some analogy, some similarity between fine roots and leaves in that they are absolutely critical to the tree for capturing needed resources. The fine roots are taking in water and nutrients. The leaves are taking in energy. But they are also expendable and replaceable, which is really good for the tree because if those most critical parts could not be replaced easily, it could be a real problem. So if the tree loses too much too fast, then that's when we get into trouble. So take care of the roots. That's a real take-home message right there. What are the best things you can do for the soil that will then lead to the roots being taken care of? I should have made that word bigger. Mulch. Mulch is anything that blankets the soil surface. It could be old blankets. It could be broken up concrete. It could be chipped up tires. It could be pecan shell. It could be grindings out of the back of the tree truck. And all of them will blanket the soil, and to some degree, they will limit the loss of water evaporating directly from the soil to the air, and they will cool the soil. But beyond that, there's a lot of differences in how they impact plant growth and tree growth. So the idea of chipped up tires. This is one of the stupidest ideas out there. And this stuff is sold as mulch. So why is it stupid? Couple of reasons. One is that material will heat up in sunlight as much or more than rock will. And so it can add a lot of heat stress to the tree. Two, it doesn't really break down quickly. And what does break down releases kind of more toxic breakdown chemicals as opposed to an organic mulch breaking down and releasing nutrients. So don't mulch with chip tires. Rock and gravel, at least they're not actively poisoning the soil, but they do definitely heat the air, and they don't break down in biological time. They break down in geological time. Well, that doesn't help. So mixed bag with rock and gravel. Generally speaking, we see a lot of problems with trees that grow in rock and gravel landscape, mulched landscapes. So then we get into the organic products. You can buy dyed wood chips that are different colors. They use a soy-based ink, so that's good. Pecan shells work pretty well. Bark works pretty well. All of these are beneficial, and some of them are more decorative than what's the best. The best is arborist chips, a mix of different species, different conditions, some of it green, some of it dead. Just think of it this way. If you walk out into a forest, a naturally growing forest, and you look at what's on the surface of the soil, it's bits and pieces of old tree decomposing at the surface. And that tends to create the kind of soil environment that is most tree root friendly. It leads to decompaction. It leads to a slow and low level available nutrient bank. Trees don't need a lot of nutrients fast. They can take a low dose, but they just need it over a long time. And it creates a soil environment that is very beneficial for the growth of mycorrhizal fungi, which can be absolute lifesavers for trees. So there's all of that. And they do cool the soil and hold the moisture in. Now, there are downsides. Chips and other organic material can move with water, can move with wind a little bit, and it may not be as aesthetically pleasing. But to me, if I can provide a mulch that makes the tree healthier, I will take the extra time to maintain the mulch that does that. I would rather have a nondescript, visually unappealing mulch of arborist chips and a really nice tree than a really poor tree in a very artistic rock mulch. It's not about the mulch. The mulch should not be the highlight of the landscape. So how do you use that mulch? This is kind of how we would do it with the city when we would plant, even in turf. We would take the turf out broadly around the planting hole. The planting hole is kind of the center of that mulched area, but we mulch beyond that so that there's less competition from the grass during the initial establishment of that tree. Now, the grass is eventually going to recolonize that, and if it's Bermuda grass, that might be tomorrow. That stuff grows in so fast. But at least it gives that tree root system an initial boost. So we want to cover a broad area. Notice this mulch ring goes out beyond the edge of the planted tree. Mulching right at the base of the trunk is kind of like watering right at the base of the trunk. It really isn't benefiting much. 3 to 6 inches of a coarse wood chip mulch is great. I have mulched deeper. I've mulched 8+ inches and it's been fine. They do talk about keeping the mulch off the base of the tree. I don't argue with that, but I also have not done it in many cases and things have been fine. I think that's more of an issue in a humid climate where there may be a lot of rain coming in and keeping too much moisture against the trunk. But for us, that's much less of an issue. The other thing that I've heard is that, like, well, during the winter, mice are going to hide out in that mulch and then they're going to chew on the trunk. And I'll tell you, if they're hungry enough to chew on the trunk, they don't care whether there's mulch there or not. So do keep it shallow around the trunk, but don't fuss too hard over that. Put it over irrigation lines. If this tree were not in turf, there would be maybe a couple of rings or maybe even 3 rings of drip tubing around that tree, and then the mulch over the drip tubing. Drip tubing directly on bare soil, mulch directly over that. No weed barrier. Crusher fines. Don't use that for mulch. Crusher fines are great if you want to create a pathway that you can that can be ADA compliant for wheelchairs. It'll mat up into a really tight kind of surface, which doesn't allow for good water penetration. It does not allow for good gas exchange because there's a lot of small clay-sized particles in crusher fines. So again, we get that compaction, and it can hold on to water really strong that should be getting into the soil below, but is actually being held in the crusher fine. All right, whew, that's just a whole lot of background. Now we're going to dial it in a little bit more to specifically what trees need. Regular and deep irrigation, broad distribution of water into the soil, mulch around the wood, the whole root system. Pruning, we could prune to reduce leaf area, which would reduce water loss, but that's also going to create wounds that take energy to deal with, and we've just taken away energy factories from the tree, so maybe not. There's a material called paclobutrazol. It's a growth inhibitor that will kind of stunt growth and at the same time appears to promote root growth underground. So that might be an option for some situations. There may well be some downsides to it. I don't know enough about using it to know what those downsides are. Wrapping it up, final thoughts. If you've got a large tree that is not well adapted here, a silver maple, a cottonwood that's not on the riverside, a catalpa, I would limit how much I'm going to expend trying to save it because it's never going to do that well. Take it out, put in something else that's going to be much more resilient. Now, I have a mulberry in the picture over here because that happens to be my favorite big shade tree for us. Unfortunately banned by the city because of the pollen ordinance, but almost bulletproof, and they get by on I don't know what water. And then use those trees in the landscape. If you've got trees on the north side of the house that don't shade your house, do you really want to spend a whole lot of time, energy, money, and water keeping them going? Or maybe take them out and put a tree on the south side of your house where it's going to shade your house and give you a benefit. All right, that's the gist of it.